You know, in April 2024, something extraordinary happened. The Dark Energy Spectroscopic Instrument DESI released its first year of data. And what it found wasn't just surprising, it was potentially paradigm shifting. For decades, we've assumed dark energy is constant and unchanging property of space itself, driving the universe's accelerating expansion at a fixed rate. We even gave it a name, the cosmological constant, represented by the Greek letter lambda. But DESI's data suggests we might be wrong. Dark energy appears to be changing over time. It's evolving, weakening, becoming, as one physicist put it, less pushy. And if this result holds up, if it strengthens with more data, we might need to rewrite our understanding of the cosmos. Let me explain what dark energy is, what DESI found, and why physicists are both excited and deeply unsettled by these results. First, dark energy. It's the most mysterious component of the universe. We discovered it in 1998 when two teams independently found that distant supernovae exploding stars used as cosmic distance markers were fainter than expected. The only way to explain this was if the universe's expansion was accelerating. Think about that. The universe isn't just expanding, it's expanding faster and faster. Galaxies are receding from each other at ever-increasing speeds. Something is pushing space apart, counteracting gravity's pull. We call that something dark energy, and it makes up about 68% of the universe's total energy content. That's more than 2/3 of everything. Dark matter accounts for another 27%. And ordinary matter, atoms, stars, planets, us, that's just 5%. We don't know what dark energy is. We don't know why it exists. But we can measure its effects on cosmic expansion, and until recently, those effects appeared constant over time. The 1998 discovery was shocking enough. Saul Perlmutter, Brian Schmidt, and Adam Riess shared the 2011 Nobel Prize for finding that the universe's expansion is accelerating. Before that, everyone assumed gravity would eventually slow the expansion down. Maybe the universe would recollapse in a big crunch. Maybe it would expand forever, but at a decelerating rate. Instead, the expansion is speeding up. And the only way to explain this within general relativity is to add a component with negative pressure, what we call dark energy. Einstein's equations allow it. In fact, Einstein himself briefly considered adding such a term, the cosmological constant, to his equations, then called it his biggest blunder when Hubble discovered cosmic expansion. Turns out it wasn't a blunder. The cosmological constant is real, or at least something very much like it is real. For 25 years after the discovery, every measurement confirmed that dark energy behaves like a cosmological constant. Its density appears constant over time, roughly 6 times 10, -10 joules per cubic meter. As the universe expands, the total amount of dark energy increases because there's more volume. But the density per cubic meter stays the same. This is weird. Normal matter dilutes as the universe expands. Dark matter dilutes. Radiation dilutes even faster. But dark energy doesn't dilute. It's a property of space itself. And as space expands, more dark energy appears to fill it. And for 25 years, the equation of state parameter W, which characterizes how dark energy's pressure relates to its density, appeared to equal exactly -1. For a cosmological constant, W equals -1 always, everywhere, at all times. It's not a field that can vary. It's a fundamental constant of nature, like the speed of light or Planck's constant. But now DESI is suggesting W might not be -1. And more importantly, W might not be constant over cosmic time. That would mean dark energy isn't a cosmological constant. It's something else, something dynamic, something that evolves. Now let me tell you about DESI, because understanding what it found requires understanding how it works. DESI is mounted on the Mayall 4-meter telescope at Kitt Peak National Observatory in southern Arizona. The Mayall has been there since 1973, but DESI, which began operations in 2021, transformed it into the most powerful galaxy mapping machine in history. Here's what makes DESI special. Most telescopes observe one object at a time, or maybe a few dozen. DESI can simultaneously observe 5,000 galaxies and quasars at once. How? Through 5,000 individual fiber optic cables, each one positioned by a robotic arm with sub-millimeter precision. Each fiber captures light from a distant galaxy, channels it to spectrographs, and produces a spectrum breaking the light into its component wavelengths. From those spectra, DESI measures redshift, how much the light has been stretched by cosmic expansion. The more redshift, the more distant the object, and the further back in time we're observing it. DESI measures redshifts with extraordinary precision, determining distances to within 1% or better. Over 5 years, DESI will map 40 million galaxies and quasars, spanning 11 billion years of cosmic history. That's an unprecedented three-dimensional map of the universe, showing how matter is distributed from the relatively nearby cosmos to the distant universe when it was just 3 billion years old. And within that map, DESI can see something remarkable: baryon acoustic oscillations, or BAOs. Let me explain what these are, because they're crucial to understanding dark energy. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Protons and electrons couldn't combine into neutral atoms because it was too hot. Photons kept knocking electrons away. And in this plasma, pressure waves traveled, sound waves essentially, propagating through the primordial soup. These sound waves were started by quantum fluctuations during inflation, tiny density variations that got amplified to cosmic scales. Denser regions attracted more matter, but the pressure of photons pushed back. This created oscillations, compressions, and rarefactions traveling outward from the overdensities at the speed of sound in the plasma, which was about 60% of the speed of light. Then, at 380,000 years, the universe cooled enough for electrons and protons to combine into hydrogen atoms. We call this recombination. Suddenly, photons could travel freely without constantly scattering off electrons. The sound waves stopped propagating. They froze into the distribution of matter. The result? Galaxies are slightly more likely to form at a certain separation. The distance sound waves could travel before recombination. That distance is called the sound horizon, and it's about 500 million light years today, accounting for cosmic expansion, stretching it from the 450,000 light year distance at recombination. This 500 million light year scale is imprinted in how galaxies cluster. If you measure the separations of millions of galaxies, you find a slight excess probability of finding pairs separated by this distance. It's like a preferred scale in the cosmic structure, a standard ruler we can use to measure distances. And here's why this matters for dark energy. The apparent angular size of this ruler on the sky depends on cosmic expansion history. If dark energy has been stronger in the past, the universe expanded faster, and distant galaxies are farther apart than expected. If dark energy has been weaker, they're closer together. By measuring the BAO scale at different redshifts, different epochs in cosmic history, DESI can reconstruct how the expansion rate has changed over 11 billion years. And from that, we can infer how dark energy has evolved. DESI's first year of data, released in April 2024, included measurements at 6 different redshift bins, spanning from z equals 0, one about 1.5 billion years ago, to z equals 2, 3 about 11 billion years ago. Each measurement gives a constraint on the expansion rate at that epoch. And when you combine all these measurements, fit them to cosmological models, and compare constant dark energy, W equals -1 always, to evolving dark energy, W varying with time, something interesting happens. The data prefers evolving dark energy. Not overwhelmingly, the statistical significance is between 2.5 and 3.8 sigma, depending on which additional data sets you include, but consistently across multiple analysis methods. The best fit model suggests W is around negative 0.7 to negative 0.8 today. And crucially, W appears to have been more negative in the past, around negative 1.2 or even lower at high redshift, and has been increasing, becoming less negative, meaning weaker over cosmic time. Let me be clear about what this means. A cosmological constant has W equals negative 1 exactly, always. If W equals negative 0.7, dark energy is weaker than a cosmological constant. It still causes acceleration. You need W is less than negative 1.3 for that, but the acceleration is less intense. And if W has been increasing from negative 1.2 inches the past to negative 0.7 today, that means dark energy has been weakening over cosmic history. It was more powerful 10 billion years ago, less powerful now, and if the trend continues, it might keep weakening in the future. Why does this matter? Because if dark energy is constant, if it's truly lambda, then we can predict the future. The universe will accelerate forever, galaxies will recede beyond our horizon, and eventually we reach heat death in 10, 100 years or more when all stars have burned out and black holes have evaporated. But if dark energy is weakening, the future is uncertain. Maybe it keeps weakening until gravity wins, the expansion reverses, and we get a big crunch. Maybe it weakens to some stable value, giving us eternal expansion at a decelerating rate. Maybe it even reverses sign and becomes attractive rather than repulsive. We don't know. And we won't know until we measure dark energy's evolution precisely. Now, I mentioned that the statistical significance is 2.5 to 3.8 sigma. Let me explain what that means and why the range exists. In science, particularly in physics, we quantify confidence using standard deviations, or sigma. If a result is 1 sigma, it's barely significant, could easily be statistical fluctuation. At 2 sigma, it's interesting but not convincing. At 3 sigma, it's evidence worth taking seriously. At 5 sigma, it's a discovery we're confident it's real. DESI's results, depending on how you analyze them, reach between 2.5 and 3.8 sigma preference for evolving dark energy over a cosmological constant. Why the range? Because DESI's BAO measurements alone can't fully constrain dark energy's evolution. You need to combine them with other data sets. The cosmic microwave background, the CMB, gives constraints on the early universe and helps anchor models. Supernova observations give independent distance measurements. Galaxy clustering and weak gravitational lensing provide additional constraints. Different combinations give different results. DESI plus CMB plus Pantheon plus supernovae, the largest, most carefully analyzed supernova data set, gives about 2.6 sigma. DESI plus CMB plus DES SN5 supernovae, a different newer supernova sample, gives 3.5 to 3.8 sigma. DESI plus CMB plus Union 3, another supernova compilation, falls in between. Why do different supernova samples give different answers? Possibly systematic errors, subtle biases in how supernovae are observed, how their distances are calibrated, how dust extinction is corrected for, or possibly cosmic variance. If the nearby universe happens to be atypical in its matter distribution, it affects local measurements. This is why physicists are being cautious. The signal is interesting, but it might be driven by systematic errors in supernova data rather than genuine dark energy evolution. And we won't know until we have more data, both more BAO measurements from DESI and more supernovae from ongoing surveys. Let me tell you about the phantom barrier crossing, because some DESI analyses suggest something even stranger than simple evolution. The equation of state parameter W equals -1 is called the phantom barrier. Below it, W is less than -1. You have phantom dark energy, which violates the null energy condition and leads to bizarre physics. Above it, W is greater than -1. You have quintessence, which is theoretically better behaved. Standard quintessence scalar field models can't cross the phantom barrier. The field's kinetic energy and potential energy constrain it to stay above -1. To cross from below to above, you need either multiple fields or exotic kinetic terms, k-essence, or modified gravity. Some DESI analyses, particularly those using certain supernova datasets, suggest W was below -1 at high redshift early universe. Cross through -1 around redshift z is approximately equal to 0, about 6 billion years ago, and is now above -1 today. If real, this crossing is extraordinary. It means dark energy's behavior fundamentally changed. It went from being phantom-like, super accelerating, leading potentially to a big rip, to quintessence-like, accelerating but controllable, leading to more benign futures. What could cause such a crossing? Modified gravity theories can do it if gravity itself behaves differently at different epochs. Multiple scalar field models can mimic crossing even though individual fields don't cross. Or maybe our theoretical understanding is incomplete and single fields can cross under conditions we haven't considered. We don't know. But if the crossing is real, it's telling us dark energy has rich, complex dynamics we're only beginning to uncover. Now let me talk about the DESI collaboration itself, because understanding who did this work matters. DESI is a collaboration of over 900 scientists from more than 70 institutions in 13 countries. It's led by Lawrence Berkeley National Laboratory, with major contributions from the University of Michigan, Ohio State, Durham, Barcelona, and many others. The Cosmology Working Group analyzing the dark energy results is led by Mustafa Ishaq Boshaki at the University of Texas at Dallas, Dragan Huderer at Michigan, and Eric Linder at Berkeley. These are some of the world's leading experts in dark energy and cosmological parameter estimation. They've been extraordinarily careful. They've tested for systematic errors, compared multiple analysis pipelines, checked robustness against different assumptions. The fact that they're publishing results showing deviations from lambda CDM, the standard model that's worked so well, indicates they're confident the signal isn't an obvious artifact. But they're also appropriately cautious. Every paper includes extensive discussion of systematics, alternative interpretations, and the need for more data. This is science done right. Report what you see, acknowledge uncertainties, and make testable predictions for future observations. We're going to explore the theoretical models that could explain DESI's results. What is quintessence? How does modified gravity work? What are cosmologically coupled black holes? And what are the challenges each explanation faces? Because finding that dark energy might be evolving as one thing, explaining why that's the real physics. And it might require new fundamental principles we haven't discovered yet. Now let me tell you about DESI. It's mounted on the Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. What makes DESI special is scale. It can simultaneously capture spectra from 5,000 galaxies at once using 5,000 individual fiber optic cables, each positioned by a robotic arm. Over 5 years, DESI will map 40 million galaxies and quasars across 11 billion years of cosmic history. That's an unprecedented 3D map of the universe, showing how structure has evolved from the early cosmos to today. And within that map, DESI can see something remarkable: baryon acoustic oscillations, or BAOs. These are subtle patterns in how galaxies are distributed, like ripples frozen into the cosmic structure. They originated from sound waves in the early universe, pressure waves traveling through the hot, dense plasma before atoms even formed. When the universe cooled enough for atoms to form, the The sound waves stopped, but they left an imprint. Galaxies are slightly more likely to be found at a certain separation, about 500 million light years today. This standard ruler lets us measure cosmic distances and expansion rates at different times in the universe's history. And that's how DESI measures dark energy's evolution. By mapping BAOs at multiple epochs from 11 billion years ago to today, we can see how the expansion rate has changed. And changes in expansion reveal changes in dark energy. Here's what DESI found in its first year of data, published in April 2024. Dark energy doesn't appear to be constant. When combined with data from the cosmic microwave background and supernova observations, the results suggest dark energy was stronger in the past and has been weakening over cosmic time. The statistical significance wasn't overwhelming, about 2.5 to 3 sigma, depending on which data sets you combine. In particle physics, we require 5 sigma before claiming a discovery, but 3 sigma is interesting. It's worth taking seriously. Then, in early 2025, DESI released more data. The data set had grown more than doubling in size, and the hints of evolving dark energy strengthened. Depending on which supernova data set you use, the preference for changing dark energy reached between 2.8 and 3.8 sigma. Still not 5 sigma, still not a definitive discovery, but getting stronger, not weaker, as more data comes in. And that's significant. Now let me tell you what changing dark energy means physically. We describe dark energy using something called the equation of state parameter W. For a cosmological constant unchanging dark energy, W equals exactly -1, always, everywhere, at all times. But if W differs from -1, or if it changes with time, then dark energy is dynamic. It's not a property of space itself, but something more like a field that can evolve. DESI's results, especially when combined with certain supernova datasets, suggest W is not constant. The current value appears to be around -0.7 to -0.8, compared to -1 for a cosmological constant. And crucially, W appears to have been more negative in the past, closer to -1 or even below it, and has been increasing, becoming less negative, meaning weaker over time. This is huge. If confirmed, it would mean dark energy is fundamentally different from what we've assumed for 25 years. It's not lambda. It's something else, something dynamic. Physicists call this quintessence, a hypothetical fifth force or field that varies over time. The name comes from medieval philosophy's fifth essence, beyond earth, water, air, and fire. In cosmology, quintessence is dark energy that can change. But there's something even stranger in the DESI data. Some analyses suggest that dark energy might have crossed what's called the phantom barrier, the divide where W equals -1. Early in cosmic history, W might have been slightly below -1 phantom dark energy, and then it crossed above -1 quintessence, like around 6 billion years ago. This crossing is bizarre. Phantom dark energy with W below -1 is problematic theoretically. It violates energy conditions and leads to weird futures like the Big Rip where everything tears apart. Quintessence with W above -1 is more theoretically well behaved. If dark energy really crossed from phantom to quintessence, that's extraordinary. It suggests dark energy isn't a single simple thing but has complex dynamics we don't understand. Now, I need to be careful here. Not all physicists are convinced DESI has found evolving dark energy. There are concerns about systematic errors, especially in the supernova data that's being combined with DESI's BAO measurements. Different supernova samples, Pantheon plus Union 3, DES, SN5, give slightly different results when combined with DESI. Pantheon plus is more consistent with a cosmological constant. DES, SN5 shows stronger preference for evolving dark energy. Why the difference? Possibly systematic errors in how distances are measured, or in how we account for dust extinction, or in other subtle effects. Moreover, some analyses suggest the preference for evolving dark energy is driven primarily by low redshift supernovae nearby objects in the last billion years or so. If you remove those, the signal weakens. This raises the possibility that we're not seeing cosmological evolution of dark energy, but rather some local effect we don't understand, maybe peculiar gravitational influences within a few 100 million light years. George Efstathiou at Cambridge, a highly respected cosmologist, has argued that the evidence isn't as strong as it appears and that we should be cautious about claiming dark energy evolves. Adam Rees at Johns Hopkins, leader of one of the teams that discovered dark energy, is also urging caution until we better understand systematic errors. So the situation is uncertain. DESI has found something intriguing. But whether it's real cosmic evolution or an artifact of systematics, we don't yet know. But here's why physicists are taking it seriously. DESI isn't the only tension in cosmology. There's also the Hubble tension, a significant discrepancy between different measurements of the universe's current expansion rate, and there are hints from other data sets, weak gravitational lensing, galaxy clustering, that lambda CDM might not be the complete story. DESI's results fit into a broader pattern of observations suggesting our standard model of cosmology might need modification, and that makes them worth investigating deeply, even if they're not yet definitive. Let me talk about what quintessence would actually be. If dark energy is a field that evolves, it must be incredibly smooth and slowly varying, otherwise we'd have detected its fluctuations already. It must couple very weakly to matter, or we'd see it affecting stars, planets, and laboratory experiments. One candidate is an axion-like field similar to hypothetical particles called axions that might also be dark matter. These fields arise naturally in some theories of fundamental physics, particularly string theory. They're light, weakly coupled, and can have the right properties to act as dark energy. Another possibility is modified gravity, the idea that Einstein's general relativity needs correction at cosmological scales. Maybe gravity behaves differently over billions of light years than it does in the solar system. Modified gravity theories can mimic evolving dark energy. Both approaches have challenges. Quintessence fields tend to be fine-tuned. You need very specific properties to match observations. Modified gravity theories often have problems with other observations or make predictions that conflict with data. But if DESI is right, we'll need something, and theorists are already exploring possibilities. Now let me address the biggest implication, the fate of the universe. With a cosmological constant, the universe expands forever at an accelerating rate. Galaxies beyond our local group eventually recede beyond our cosmic horizon. In trillions of years, the universe becomes cold, dark, and empty, the heat death. But if dark energy is weakening, as DESI suggests, the future might be different. If it continues weakening, it might eventually lose its battle against gravity. The universe could stop accelerating, start decelerating, and eventually recollapse a big crunch. Alternatively, if dark energy continues weakening but never reverses, we might end up with a universe that expands forever but at a decelerating rate, more like the pre-1998 expectations. Or, and this is wild, if dark energy strengthens instead of weakens, we could head toward a big rip where acceleration becomes so strong that galaxies, stars, planets, atoms, and eventually even space itself tears apart. We don't know. The future depends on dark energy's evolution, which we're only beginning to constrain. We're going to dive deeper into the physics. What are the theoretical models that could explain DESI's results? What are the challenges they face? And what observations from DESI's future data releases, from other experiments, from different techniques will help us figure out if dark energy really is evolving. Because this isn't just about cosmic expansion or the universe's fate. This is about understanding the dominant component of reality, the 68% of the universe that we barely comprehend. And if it's changing, we need to know how, why, and what it means. So we've established that DESI found hints, strong hints, but not yet definitive proof that dark energy is evolving over cosmic time. Now let's explore what that actually means and what models could explain it. Let me start with quintessence, because it's the leading theoretical framework. Quintessence is a scalar field similar to the Higgs field or the inflaton field, thought to have driven cosmic inflation. This field pervades all of space, and its energy density varies slowly over time as the field rolls down a potential energy curve. Different potential shapes give different evolution. A thawing quintessence model has the field initially frozen, behaving like a cosmological constant, and then starting to roll recently, causing W to increase dark energy weakening. This matches DESI's hints. A freezing quintessence model has the field rolling initially and then freezing into a constant value. This doesn't match DESI as well. There's also tracker quintessence, where the field's energy density tracks the matter density for a while before becoming dominant. This can produce interesting evolution patterns. The key property distinguishing quintessence from lambda is that W can vary. For quintessence, W is constrained between -1 and +1, though usually between -1 and -1,3 for cosmic acceleration. The DESI results, showing W around -0.7 to -0.8 today, and more negative in the past, fit quintessence naturally. But there's a problem: the phantom barrier crossing. Some DESI analyses suggest W crossed -1 from below to above. Standard quintessence scalar fields can't do this. They're constrained to stay above -1 by energy conditions. To cross the phantom barrier, you need phantom dark energy fields with unusual kinetic energy terms that violate standard energy conditions. Or you need multiple fields that can mimic phantom crossing, even though individually they don't cross. Or you need modified gravity that effectively produces a crossing. All of these options are theoretically challenging. Phantom fields lead to instabilities and strange physics. Multiple fields require fine-tuning. Modified gravity has its own problems. So if the phantom crossing is real, we have work to do theoretically. Now, let me tell you about an alternative explanation that doesn't require new fields: cosmologically coupled black holes. This is a speculative but fascinating idea proposed by Duncan Farah and collaborators in 2023. The idea is that as the universe expands, black holes grow, not by accreting matter, but by coupling to the expansion itself. They're cosmologically coupled, drawing energy from the expansion. And as they grow, they contribute to dark energy. In this model, dark energy isn't a field, it's the collective effect of all black holes in the universe. And as black holes merge and evolve, the dark energy they contribute changes. This could produce varying W. The DESI data has been analyzed in light of this model, and it fits reasonably well, but it's controversial. Many physicists are skeptical that black holes can couple to cosmology this way without violating known physics. But it's being taken seriously enough to warrant investigation. Another possibility: interacting dark energy and dark matter. Maybe dark energy and dark matter aren't separate. Maybe they interact, exchanging energy. As dark matter's density decreases due to expansion, the interaction changes, causing dark energy to evolve. This coupled quintessence model can produce interesting dynamics, including apparent evolution of W. And intriguingly, Some versions can help with the Hubble tension by allowing faster expansion in the early universe. They reconcile different Hubble constant measurements. DESI data has been analyzed with coupled dark energy models, and they fit well. But again, the interactions must be very specific to match all observations, which raises fine-tuning concerns. Now let me address modified gravity more seriously. Instead of adding a quintessence field, maybe Einstein's general relativity needs modification at large scales. There are many proposals: FR gravity, scalar tensor theories, massive gravity, extra dimensions. Let me explain FR gravity first, because it's one of the simplest modifications. In standard general relativity, the action, the mathematical expression we use to derive Einstein's equations, contains a term proportional to r, the Ricci scalar curvature. In FR gravity, we replace r with some function FR. Different choices of FR give different physics. A popular choice is FR equals r plus alpha r squared, where alpha is a small constant. This extra r squared term is negligible in strong gravity regions like near black holes or neutron stars, so it doesn't affect solar system tests. But at cosmological scales, where curvature is tiny, the r squared term can become important and drive acceleration. The beauty of FR models is they can mimic dark energy without actually adding dark energy. The acceleration comes from modified gravity, not from a new component. And some FR models predict evolving effective equation of state, exactly what DESI is seeing. But FR gravity has problems. Many models are unstable. They predict ghosts, negative energy states, or other pathologies. The viable models require very specific functional forms that seem fine-tuned, and they must pass stringent tests from galaxy dynamics and gravitational waves. Scalar tensor theories are more general. Here you add a scalar field phi that couples to the Ricci curvature. The field's value determines the effective strength of gravity. As the field evolves cosmologically, gravity's strength changes, affecting expansion. The most general scalar tensor theories are called Horndeski theories, after Gregory Horndeski, who classified them in 1974. They include a wide range of models, from simple Brans-Dicke theory to complex non-minimally coupled scenarios. Ed Copeland and collaborators at the University of Nottingham have shown that certain Horndeski theories fit DESI's data remarkably well. Specifically, models where the scalar field couples non-minimally to curvature, meaning the coupling strength itself depends on the field's value, can produce the observed WZ evolution while avoiding instabilities and passing solar system tests. The key is in the coupling function. If it's chosen correctly, the field's evolution naturally produces W that starts around -1.2 at high redshift, crosses -1 around Z, is approximately equal to 0.5, and reaches -0.7 today. This isn't arbitrary. The coupling function is constrained by requiring the theory to be mathematically consistent and observationally viable. Now let me talk more about cosmologically coupled black holes, because this 2023 proposal by Duncan Farah and collaborators is genuinely radical. The idea is that black holes don't just grow by accreting matter, they grow with the universe itself. In this model, the mass of a black hole M scales with the cosmological scale factor A, according to M, is proportional to AK, where K is a coupling parameter around 3. As the universe expands, A increases, black holes grow. This growth isn't from eating nearby matter, it's from coupling to the cosmic expansion itself. Where does this extra mass come from? From the vacuum. In quantum field theory, the vacuum has energy, and if black holes couple to this vacuum energy, they can extract mass from it. This sounds crazy, but some interpretations of black hole thermodynamics suggest black holes and cosmological horizons are intimately connected. If true, this has remarkable implications. As black holes grow, they contribute to the universe's energy density. And because their number density decreases with expansion while individual masses increase, the net effect is an evolving dark energy component. The DESI data has been analyzed assuming cosmologically coupled black holes, and the fit is surprisingly good. The model predicts W evolving from about negative 1.3 at z equals 2 to negative 0.7 today, matching DESI's hints. But most physicists are skeptical. How exactly do black holes couple to cosmology? What's the mechanism? Does it violate energy conservation? These questions remain unanswered. Farah's team argues the coupling is allowed by general relativity under certain interpretations, but many experts disagree. Nevertheless, the idea is being taken seriously enough to warrant detailed investigation. If nothing else, it shows that DESI's results are stimulating creative theoretical thinking. Let me now give you specific numbers on the different supernova data sets, because understanding their differences is crucial to assessing DESI's claims. Pantheon Plus is the gold standard 1,701 Type Ia supernovae, carefully calibrated and analyzed by a large collaboration. When combined with DESI plus CMB, it gives about 2.6 sigma preference for evolving dark energy. This is interesting, but not conclusive. DES SN5 is a newer data set from the Dark Energy Survey, 1,635 supernovae observed with a single telescope system, reducing some systematic errors. Combined with DESI plus CMB, it gives 3.5 to 3.8 sigma preference, much stronger. Why the difference? Possibly because DES SN5 has better control of certain systematics, or possibly because it has different systematic errors that happen to favor evolution. Union 3 combines multiple supernova data sets, 2,087 supernovae from many sources. It's the largest compilation, but potentially more susceptible to systematic differences between data sets. With DESI plus CMB, it gives about 3 sigma preference. The fact that different supernova samples give different answers is concerning. It suggests systematic errors might be driving at least part of the signal. This is why Adam Riess and others urge caution. Until we understand why the data sets disagree, we can't be confident the evolving dark energy signal is real. Let me talk about weak gravitational lensing, because it provides completely independent constraints on dark energy. When light from distant galaxies passes near massive structures, its path bends slightly. This distorts the galaxy's shapes in systematic ways we can measure. By mapping these distortions across the sky, we can reconstruct the distribution of dark matter and measure how cosmic structure has grown over time. And growth rate depends on dark energy. More dark energy means slower growth because it counteracts gravity's clumping. The Dark Energy Survey, the Kilodegree Survey, KIDS, and the Hypersuprime Cam HSC survey have all measured weak lensing. When the results are combined with DESI, they show mild preference for evolving dark energy around 2 to 2.5 sigma. Not as strong as some supernova combinations, but consistent with the general picture. Moreover, weak lensing shows its own tension with lambda CDM. The amplitude of matter fluctuations measured by weak lensing is slightly lower than predicted by the CMB assuming lambda CDM. This is called the S8 tension. If dark energy was stronger in the past, more negative WA, it would suppress structure growth, potentially explaining the low S8. So evolving dark energy might simultaneously explain DESI's results and the S8 tension. This is circumstantial evidence that we're onto something real. Multiple independent tensions pointing toward the same modification would be remarkable. We're going to explore what all this means for the future. What specific scenarios could play out? What will Euclid, Roman, and LSST measure? How will we know if dark energy is really evolving? And what does it mean philosophically that the dominant component of reality is something we still barely understand? Let me talk about the Hubble tension, because it's intimately connected to dark energy evolution. The Hubble constant, the current expansion rate, has been measured two ways. Early universe measurements from the cosmic microwave background give about 67 kilometers S minus PC. Late universe measurements from supernovae and Cepheid variables give about 73 km SMPC. This 9% discrepancy is statistically significant over 5 sigma. One of them must be wrong, or our model is missing something. Evolving dark energy could help. If dark energy was different in the past, it affects how we interpret early universe measurements. Some quintessence models reduce the Hubble tension to 2 to 3 sigma, still there, but less severe. The DESI analyses show this. When they include evolving dark energy, the tension with local Hubble measurements decreases significantly. This is circumstantial evidence that dark energy evolution might be part of the answer. But, and this is important, not everyone agrees. Some analyses show that when you carefully account for systematics in supernova data, the Hubble tension doesn't improve much. The low redshift supernovae driving the dark energy evolution signal might be the same supernovae causing problems with Hubble tension. If those measurements are systematically off, fixing them might resolve both issues without needing evolving dark energy. Now let me tell you what's happening next observationally. DESI is still operating. By the time it finishes in 2026, it will have 5 years of data, more than double what's been analyzed so far. More data means better statistics, smaller error bars, and hopefully clarity on whether the evolving dark energy signal strengthens or disappears. Additionally, several supernova surveys are underway. The Pantheon Plus team is working on improved analyses with better systematic error control. The Dark Energy Survey is analyzing more supernovae. The Zwicky Transient Facility is finding nearby supernovae that can probe recent dark energy evolution. And there's LSST, the Vera C. Rubin Observatory in Chile, which will begin operations soon. It will discover tens of thousands of supernovae per year, providing unprecedented statistics for constraining dark energy evolution. There are also weak gravitational lensing surveys measuring how dark matter distorts background galaxy images. These provide independent constraints on dark energy and cosmic expansion. The Dark Energy Survey, the Hypersuprime CAM Survey, and upcoming Euclid and Roman Space Telescope observations will all contribute, and CMB measurements continue improving. The Simons Observatory and CMB S4 will measure the microwave background with higher precision, better constraining early universe parameters, and providing tighter comparisons with late-time observations. All of these data sets will come together over the next few years. By 2027 to 2028, we'll have significantly more data than we do now. And that data will either confirm DESI's hints or show they were statistical fluctuations or systematics. Let me talk about what confirmation would mean for physics. If dark energy really is evolving, it means the cosmological constant is wrong. Lambda CDM, our standard model, would need replacement. This would be the biggest change to cosmology since dark energy's discovery in 1998. We'd need to identify what dark energy actually is, a quintessence field, modified gravity, something else entirely. We'd need new fundamental physics, and it might connect to other mysteries. Why does dark energy have the value it does? This is the cosmological constant problem. Lambda's value is 10, 120 times smaller than naive quantum field theory predicts. If dark energy is dynamic, maybe there's a mechanism that drives it to small values naturally. And there's the coincidence problem. Why are dark energy and dark matter densities comparable today? In lambda CDM, this is a coincidence. They've been converging over cosmic time and happen to be similar now. In some quintessence models, there are attractor solutions where they naturally become comparable. So evolving dark energy might solve multiple problems at once. But if the signal doesn't strengthen, if it turns out to be systematics or statistics, then lambda CDM survives. And we're back to the question, what is the cosmological constant and why does it have the value it does? We're going to look at the philosophical implications. What does it mean for the universe's fate? How does it affect our understanding of fundamental physics? And how should we think about a cosmos dominated by something we barely understand and which might be changing in ways we're only beginning to grasp? So here we are. DESI has found hints tantalizing, strengthening, but not yet definitive that dark energy is evolving. If real, this rewrites cosmology. If not, we still face the mystery of the cosmological constant. Either way, we're grappling with deep questions about the universe's nature and fate. Let me start with the fate of the universe, because it's the most direct consequence of dark energy's evolution. If dark energy is a cosmological constant, the future is bleak but predictable. The universe expands forever, accelerating endlessly. Galaxies beyond our local group recede beyond the cosmic horizon. We lose contact permanently. Star formation eventually ceases as gas is exhausted. Stars die, black holes evaporate, and after 10, 100 years or more, the universe reaches maximum entropy heat death. But if dark energy is weakening, as DESI suggests, the future might be different. If it continues weakening indefinitely, the acceleration slows. Eventually, gravity might win. The universe could stop expanding, reverse, and recollapse in a big crunch. Or dark energy might weaken to a stable value, leaving us with eternal expansion, but at a decelerating rate like the pre-1998 expectations. Alternatively, though, DESI doesn't suggest this, if dark energy were strengthening, we'd face a big rip. Acceleration becomes so strong that it tears apart first galaxies, then stars, then planets, atoms, and finally space itself. That's not what current data suggests, but it's theoretically possible with phantom dark energy. The point is, we don't know the future, and we won't know until we understand dark energy's evolution better. Now let me talk about something profound, the anthropic principle and dark energy. The cosmological constant's value is puzzling not just because it's tiny compared to theoretical expectations, but because it's apparently fine-tuned for life. If lambda were much larger, the universe would have accelerated so early that galaxies couldn't form. No galaxies, no stars, no planets, no life. If lambda were much smaller or negative, the universe might recollapse before life could evolve. The range of values compatible with life is narrow. This has led some physicists to invoke the anthropic principle. We observe a life-compatible value because we couldn't exist otherwise. In a multiverse with varying lambda, we necessarily find ourselves where it's right for life. But if dark energy is quintessence dynamic and evolving, then maybe its value isn't fundamental. Maybe it's determined by field dynamics. And those dynamics have attractor solutions that naturally produce small, life-compatible values. This would eliminate the fine-tuning problem. Or maybe not. Maybe quintessence also requires fine-tuning in its potential shape or initial conditions. We don't know yet. Let me address something philosophical. What does it mean that 68% of the universe is something we don't understand? For most of human history, we didn't understand much. Lightning was mysterious, the stars were mysterious, life was mysterious. Gradually, science explained these things. We've made enormous progress. But dark energy humbles us. It's not a small effect we can ignore. It's the dominant component of reality driving the universe's evolution. And after 25 years of study, we still don't know what it is. Some philosophers argue this shows science's limits. Maybe some things are inherently unknowable. Maybe the universe is fundamentally beyond our comprehension. I don't buy that. I think we're in a transitional period. Yes, we're ignorant about dark energy now, but we're gathering data, building experiments, testing theories. DESI's results, whether they confirm evolving dark energy or not, are progress. Every constraint we place is understanding. Science doesn't require that we know everything immediately. It requires that we keep asking questions, keep testing, keep refining our understanding, and we're doing that. Now let me talk about what I think will happen over the next few years. DESI will continue operating, gathering more data. By 2026, we'll have the full 5-year data set, 5 times more data than the first-year results that sparked this excitement. If the evolving dark energy signal is real, it should strengthen, statistical significance should increase, the preference for quintessence over lambda should become overwhelming. But if it's systematics or statistics, the signal might weaken or disappear. More data could dilute the effect, or improved systematic error control could show the preference was an artifact. My guess, and it's just a guess, is that the truth is somewhere in between. I think there's a real signal suggesting dark energy isn't perfectly constant, but I think the effect is more subtle than the most exciting analyses suggest. Maybe W varies slowly, or maybe there are small deviations from -1 that don't require quintessence, but rather some correction to lambda CDM. We'll know soon. And knowing is what matters. Let me close by reflecting on what this moment represents. We're at the frontier of cosmic understanding. We have extraordinary tools, DESI, LSST, Euclid, Roman, CMB, observatories. We're measuring the universe with precision our predecessors could only dream about. And we're finding tensions, anomalies, hints that our model might be incomplete. The Hubble tension, Webb's massive early galaxies, DESI's evolving dark energy. None are definitive yet. All could be wrong, but they're pointing toward something. Maybe they're telling us lambda CDM needs modest corrections, a few parameters adjusted, a complication added. Or maybe they're telling us we're missing something fundamental. I don't know which, but I know this. We're living in an era of discovery. The next decade in cosmology could be transformative. We could have a new standard model. We could understand dark energy's nature. We could resolve the Hubble tension. We could connect cosmology to particle physics and quantum gravity. Or we could remain puzzled, needing more data, better theories, deeper insights. That's okay too. Science is a process, not a destination. What I find beautiful is that the universe still surprises us. After centuries of study, after mapping billions of galaxies, after measuring the cosmic microwave background to exquisite precision, we're still finding new mysteries. Dark energy might be evolving, and if it is, that's extraordinary, a fundamental component of reality changing over cosmic time, revealing dynamics we didn't expect. And if it's not, if it's lambda after all, that's also extraordinary because it means the cosmological constant is even more finely tuned and mysterious than we realized. Either way, we're confronting something profound. The universe is teaching us that we don't understand it yet, and that's an invitation to keep exploring, keep questioning, keep pushing the boundaries of knowledge. DESI found something interesting. Whether it's revolutionary or not, we'll know soon. But the process of finding out, that's what makes science beautiful. The questions, the data, the debates, the gradual convergence toward truth. We live in a universe dominated by dark energy. It's driving cosmic expansion, determining the universe's fate, and shaping the large-scale structure of everything. And we're finally, after 25 years, beginning to understand it might not be constant. That's progress. That's exciting. And that's pretty amazing. The universe is 13.8 billion years old. You're living in the brief cosmic moment when intelligent life first arose and started asking questions about dark energy. And you're here precisely when we might be discovering it's not what we thought. That's pretty special. And whatever DESI's final answer turns out to be, we're participants in one of the great detective stories in human history, figuring out what reality is made of, one observation at a time. The dominant component of the universe might be changing, and we're the first beings to notice. That's pretty amazing.